So therefore, if you look at this, implementation that we have till now, right? We have the whole implementation shown here. The blue component is the control unit that we are going to discuss at this point, right? So what is the control unit? It is basically going to decode this instruction and generate these signals appropriately. The control unit is a purely combinational block that is going to take the first 6 bits of the instruction 0 to 6. Then it needs function 3. So this is the OP of the instruction, first 7 bits. Then function 3, which is 12 to 14. Okay. Then you have function 7 of 5. Okay. The function 7 bit, we are going to take only the 5th bit there. Okay. And then we also have the 0 flag here, right? Now all of these, a combination of these is going to be used to generate various values for these output control signals, because ultimately depending on these 1, 2, 3, 4, 5, 6, 7 control signals, every single operation of the RISC V can sort of be handled, at least the subset that we were talking about till now. Okay. So with that, let us jump into the single cycle control implementation, right? So like I told you, the high level view is as follows: 6 to 0, 14 to 12 and bit 30, right? So this function 7 we will come to a little later, why bit 5th bit and all that, right? And you have this PC source, result source, mem write, ALU control, ALU source, immediate source and reg write. Okay. So the first thing to do is to figure out, you have the main decoder. Remember, we always discuss that the first thing you have to do in the instruction is to take the lowest 7 bits 0 to 6 and understand what type of instruction is it, right? Whether R type, I type, how, everything. So that is the basic block. It's a main decoder that is needed to decode that instruction, right? So you decode this, right? And then based on this main decoder, you are going to generate the result source, okay? The mem write. So whether you do a mem write or not is going to be determined whether it's a store type instruction or not, right? The result source, right? If you look at result source, it's basically the the control that is going to select this mux, whether you're going to choose between memory reading from memory or the register ALU output itself, right? And after that you have the ALU source again here, right? ALU source is going to choose between the basically that is this mux here, okay? ALU source is going to choose between register data for as the second operand to the ALU or immediate data, right? And then IMM source, like I told you, is the control that is going to choose how to interpret the instruction in order to get the 32 bits of immediate data, right, including sign extension. Finally, whether you do reg write or not, again, is determined whether it's an R type of instruction or not, right? So this is going to also generate the ALU OP, okay? And based on function 3, 2 to 0, function 7, 5, right? The ALU decoder is going to sort of give you the ALU control 2 to 0. So what is ALU control? So if you look at it, that is this 3 bits. The ALU, some 8 operations you can do in the ALU, and that is going to be determined by this. Okay. So now what we are going to do is, we have the OP value here, okay, 3, 35, 51, 99, and the instruction load word, store word, R type, BEQ and all that, and we are going to now populate what the value of this 1, 2, 3, 4, 5, 6, 7 control signals are going to be, right? So if you look at this, the ALU, right, the RISC does not allow all sorts of operations, right, intentionally, right? So what happens is, in the RISC V, apart from the load store type of architecture where you isolate memory from ALU operations, which is a very good thing. You also don't allow all sorts of arithmetic operations. It becomes easier to implement, and more importantly, much easier to test such a processor when you want to design and fabricate such a processor in reality. Okay, so the ALU control 2 to 0 is basically like this. Okay, this is the output, by the way, of the control block, right? 0 0 0 is add, subtract, and, or, and shift left, right? That's all. So you get some answer here. So therefore this is very, very straightforward. All you are doing is using the ALU control in order to implement various arithmetic operations that we just discussed, right? So that's a very straightforward thing. So you either do addition, you do subtraction, and so on, right? Now let's now get into the ALU decoder. Okay, so so how are we basically getting this? So you look at this ALU control, add, subtract, and so on, right? So if you look at load word and store word, typically you are only doing addition operation, because the immediate data is going to take care of subtraction. That can be a negative number, right? And therefore you just need addition out there. So it doesn't matter what this this OP5 bit, function 7 bit and all this, right, for you. Okay, just ALU OP of 00 will basically tell you that this is an add instruction that you want, right? Now for a branch and equal, what are you going to do? Branch and equal, by default it is a subtract operation, because you are subtracting two registers. Depending on whether they are equal or not, you are doing some branching if necessary. So therefore this also is just, it doesn't matter what this is. ALU op is 0 1, then the operation has to be a subtract, nothing else. Now if it is 1 0, right, ALU op, remember ALU op is an input to this decoder, ALU decoder, right? Now you are going to use the function 3 like this, okay, and the OP5 and function 7 of 5 to determine whether you want to do various operations like this. So you can do an add, subtract, set less than, it's not shift left, sorry, and or, and, okay. So based on this choice you can achieve these functionalities in your ALU. So typically this will be used, it's very obvious, for the register type of instructions, because that's when the ALU is going to get excised for all types of operations. Okay, so let us look at an AND type of operation. What is it? It's an R type, right? I mean, let's look at an AND operation, and it's an R type of instruction, right? So you have OP is 51. So what do you want to do? You want to do AND X5. So you want X5, right, X5 to be equal to X6 and X7, right? This is the bitwise AND that you want. That means you have to do a register write back into X5. You have to read X6, you have to read X7. That means the ALU, the two operands has to be the two register values, right? And you have to bypass the memory in order to write this data back into register X5. Therefore, if you look at this blue path, right, that you see here, it's essentially the path that needs to be exercised for this instruction. Okay, you go through the instruction memory, you go through this, right, then you read register data RS1, then RS2, you get it onto RD1, RD2 respectively. Then you don't read the immediate data, you get the source value, and source B is going to be the register data. Source A is of course RD1. ALU will perform that operation, and then you bypass the memory like this, okay, through that mux, and then come back with the result and write it back into my destination register. So in order to achieve this, obviously my register write has to be 1, okay, because I need to write back into that register. Okay, my immediate source, right, what is this value? It basically, really, this doesn't matter. immediate source is not going to matter, because this mux is going to take care of bypassing that completely. Okay. Now ALU source of course has to be 0, otherwise I will read that immediate data, right? Then my ALU control has to be 0, 1, 0, because I want the AND operation there, right? So if you look at it, the AND operation, we wanted ALU control, right? So let's look at this. Yeah, this one, you wanted 0, 1, 0, and therefore this has to be 0, 1, 0. Memwrite has to be 0, because you don't want to write to memory. The result source, of course you have to bypass the data that is read out of the memory and take the ALU operation answer that has to be written back. PC source obviously has to be 0, because there is no branching. The next instruction is at PC plus 4, okay, and therefore that's why you achieve this kind of a truth table, right? This is basically a truth table that we have essentially for R type, okay.